So after we went through all those vellum constraints last time, some of you guys wanted to talk about the grain constraints and asked if we could talk about grain constraints. And I'm afraid we can't, because technically grains don't have constraints. But semantics aside, let's talk grains in vellum. So let's just drop down a GeoNode, dive in there, stick with the torus for now. 24 rows, 48 columns, maybe dial down the radius just a tiny bit, and let's just rotate it around 30 degrees on each axis, like this. And now in order to do grains in vellum, let's drop down a vellum configure grain node here. Let's wire this in, highlight it, and nothing really happens. But as soon as we check create points from volume, we can see we kind of rasterize our incoming geometry into those points, which all have this neat little sphere sprite mapped to it, so we can see our individual grains here. Let's dial back the grain size a bit, and the mass too. If we uncheck add sprite material, we can just see the points. Also, this is a bit too regular for my taste, so this has a good bit of aliasing in it. Let's just enable jitter scale and set it to 1 to get a bit more of an irregular pattern here with my points. What happened here? Let's have a look. Let's drop down a null, wire this into our simulation geostream first and middle mouse on it. And we can see we have a few point attributes set here. IsGrain, mass, our position, our p-scale, our sprite shop, sprite UV, and V. Let's just head into the geo spreadsheet and have a look at them in detail. So the isGrain is set to 1, and that just lets vellum know that each of those points should be handled as a grain, so as an individual particle. The mass, we set that within the vellum constraints grain here, and the p-scale is basically half of the grain size that we set up here. Sprite shop is just the path to the sprite material, so to our spherical sprite here. Sprite UV, our UV coordinates, and we have a velocity here. 3 components, x, y, and z. Let's have a look at the constraints that we actually generate, the constraint geometry here. And when middle mousing on it, we can see we did not generate any constraints here. We have just our point position, and on our primitives there are no attributes. Actually, there are no primitives either, because what grains is just pure position-based dynamics without any constraints. We can add some later, but the basic setup is just no constraints. So individual points, individual particles here. Let's drop down a vellum solver and see how this looks in simulation. Let's check a ground plane and move it down to say -2, and let's just hit play for now. And what we're seeing here in the simulation is clearly a wild behavior. So the bounciness is too high, everything explodes as soon as it hits the ground. So what should we do? The trick with grains in vellum is to increase the substeps. SideEffects recommends a substep setting of at least 5 substeps, and depending on the simulation, you might still have to increase this. So I have had good experiences with 10 substeps, while all the way decreasing the constraint iterations to 10. So this will simulate a bit slower, but it is going to simulate more correctly, a more physically plausible behavior. So that's what we're getting with increased substeps. And that's about the only trick there is to grains in vellum. It's just keep in mind to increase your substeps to enforce a more physically plausible behavior of your individual particles. Now, the next question that usually pops up in conjunction with grains is, can I do clumping? Or how do I do clumping? And yes, in fact you can do, and that's where constraints come in. So the vellum constraints grain sub only sets the isPBD attribute on our particles and does not care about constraints. So each of those particles is moving individually and just trying to avoid other particles and other colliders, that is. However, if we want to simulate clumping, or if we want to have clumping, we need to kind of connect those individual particles. I'm going to do this with the help of a vellum constraint sub. Wire this in between here in the solver. Let's reset our simulation. Let's set this constraint up to be a glue constraint that connects points to points. And let's drop down a null. Again, before the grains, when we highlight this, it does not generate any primitives, it does not generate any constraints. When we wire in the glue, we can see we now get those connections here between individual points. So let's dial this in. Down here, let's increase the constraints per point to say 3 or 4. And let's just run the simulation as is. So now we've got this main mass that is connected by these constraints and stays together really well, with a few individual particles that hadn't been connected to any other geometry and can stray away from the main mass. However, that is only somewhat convincing, so let's down here enable the breaking, and let's decrease the breaking threshold a good bit, say 0.005, and also maybe decrease the stiffness to say 100,000, and hit play again. And I think we can decrease the breaking threshold a good bit more, 0.001. Let's decrease it further. Yeah, that looks a bit better. So we have these areas that stick together, but still break from the main mass. What's kind of annoying with this threshold here is that when we highlight the constraints here and go to the geo spreadsheet and on our primitives tab, the break threshold is the same for every connection that we have in between those particles. And to make this a bit more organic, what I'd like is an individual threshold per primitive. And I'll just wrangle this together by dropping down a primitive wrangle, wiring this after the null in here. And what I want to do is, let's middle mouse on this, I want to influence the break threshold attribute. So float break threshold times equals. So we want to multiply this with a value of, say, between 0.1 to 1. The break threshold should be randomly scaled between 10% of its original strength and 100% of its original strength. And let's do that by fitting a random number that is usually between 0 and 1. And let's use the primitive number here plus some seed. And let's fit that between 0.1 and 1.0 like this. Let's highlight this and head to the geo spreadsheet, and we can see the break threshold is now different for each primitive here. Let's wire this back into our solver, highlight the solver, reset the simulation, and hit play. So now we've got a bit more of an organic behavior going on in here. What I could do is dial back up the break threshold a bit, because I'm scaling it down here and there. So maybe let's increase it back, but in general, that's the technique I'm using for clumping here. There is one more thing that I'd like to show you. Let's wire in the vellum constraints directly back into the solver and reset the simulation. What I could do with the vellum constraints glue here is cluster these points and clump them individually, depending on their individual cluster centers. So let's drop down a cluster points sub here, and after the vellum constraints, let's wire this in here, highlight it, and you can see, I mean, these are 10 clusters, so let's increase them to maybe 40. So we got those 40 individual clusters here. Middle mouse on them. You can see we have a cluster number written to each point, so each point stores the ID of its cluster it belongs to, and let's pipe that into our glue constraint here. Highlight it, let's disable breaking for now, and up here in the glue search, let's just check cluster attribute, and this is already set up to read in the attribute that we've written onto the points using the cluster point sub. So let's just highlight the vellum solver, hit play. And we can see now we've got those individual clusters sticking together and sliding around. So that is how you do the basic vellum grain setup and how you do basic clustering in vellum grains.